All right, so we're on 2B.6 part B of our notes. And by all of this is said and done, you should be pros at regressions and residuals, right? Yeah? Uh-huh. Yeah, we should. All right, so up first, here we have an example. The total number of views for a popular podcast is increasing. The table shows the estimates of the total views each month since January 2010. Use a graphing calculator to find a quadratic exponential power regression model. I am supposed to be encouraging the use of Desmos a little bit more, just in case someone really needs it or is going to be comfortable with it. Where is that problem? Oh, we did this last, right? Hello. Where are we at? Oh, we did do 6, didn't we? Sorry, my bad. We're here on this one. Sorry. Tricked you. We didn't do 6. It's the quadratic review. It's fine. We don't need it. It was for you to do it, not me. Sorry. Here we go. All right, your biology teacher has bacterial cultures for a class of 24 students. Each student is measuring the number of bacteria Y in his or her culture at intervals of time X hours during the day. The results are shown below. Okay, we're going to be talking about a power function regression model. So we've done linear, quadratic, and exponential, correct? Okay, today we're focusing on power and cubic models. Power function models in your Desmos, I'm going to write that rule down. So if we're doing a power function in Desmos, it is simply going to be y1 squiggle, and it's just a, and it's going to be x to the b. Okay, so in Desmos, when you're looking for a power function, it's a little different, right? Because you don't know what your power is, and you want Desmos to figure out what is your power. Oh, there needs to be a 1 on your x. I apologize. Okay, there we go. All right, so the reason why I'm going to do this in Desmos is just because it's a lot of typing for me to do it on the calculator. It's faster for you to type it on the calculator, but it's not as fast for me. So I want to make sure that we are comfortable doing this in Desmos and that we are understanding what we're typing in. The other thing is remembering for exponential, I know these can look and feel the same, but they're different. So in Desmos, your exponential is going to be y1 tilde a times b to the x1. Do we see the difference in them? Yes. The placement of the x and the b, they switch. Okay. So the difference between the power and the exponential on Desmos is slightly different, but there is a difference, and I want to make sure we are comfortable and understand that difference. Yes. Anyone's like, I don't see the difference. Okay, perfect. Obviously on TI-84, it says PW and it says exponential. So that difference in Desmos in TI-84 is a little more obvious. So if you have your handheld calculator and you go to stat calc, you're going to scroll. To me, it's faster to just scroll up. But if you scroll up, you'll see where it says exponential is 0 and power is A. Easy enough? Okay. But in Desmos, be careful how you input. All right. So let's go ahead and give that a shot. We're going to try it. What I do want to do is be more intentional about the Desmos that I use. I'm going to, they haven't given an exact one for your AP test, but to my understanding, it's going to be the same Desmos that they allow in the SAT, which is why if you go to your modules page, I put the link to that calculator. So it's the Desmos calculator that, under course, that will either be using for sure, or I'll be at some version of this one. So whatever settings and limits are here are the ones that we'll be able to use. Oh, they did update it. See? So it says CB, SAT, and AP. So this is the one that'll be in the digital test. So if you are going to continue to use Desmos, I want to make sure that you're using the one that you're going to see. Make sense? Okay. So here, notice that we only have these features. It takes away some of the features and I believe some of the functions that are normally there, but it's very minimal that are gone. Everything else should be present. But this is the one that you'll be able to use on the test. Okay. So I'm going to add my table. Once I add my table, Then we'll go from there. So I'm going to take time putting in the table. It's going to take a moment. So you put in your table, I'll put in my table, and then we will come back together. All right. Mhm.
Wait, where do you get the maps?
All right. It's two column. It's just one big table.
Oh, okay.
All right. So now I've put in my data. Beauty about Desmos is that you hit the zoom fit and it's going to adjust your window automatically for you to see your data. So here's my data. All right. And now we're going to test out the two functions. So we're going to look at the power and we're going to look at our exponential. So starting with the power function, remember y1, and this is going to be ax1 shift 6 to carry the b. That's your power. And when we're on Desmos, we want to make sure we check the what? The log box. Okay. Make sure you are checking the log box when you're utilizing Desmos. Okay. So there's my equation.
What's up?
Hmm?
Good question.
Yes.
Should that be one color or two, three?
What do you mean?
Because this one take the table of ask for a color.
Mine is just one.
Oh.
Okay, so then our exponential model is y1 tilde a times b shift 6 x to the 1. And I'm going to make sure I check the log box. So now I have both models. I have my power model and I have my exponential model. And I'm going to write them down. Is that cool? How do we feel about using Desmos for larger data sets? And are we comfortable with the difference between the exponential and the power in Desmos? Yes? Okay. All right, I'm going to switch back so I can write down my answer, if that's okay. All right, so my first one, I have my first regression, I'm going to call it y hat equals 291. And I'm going to truncate it on the fourth. So I'm going to do, huh? No, you can, as long as you round correctly. No, you're gonna have to have at least only three, or you can do 3 to 4 significant. Yes, make sure you're in log mode. Okay, and then this is gonna be x to the 1.2207. Can't remember. If I'm just gonna truncate it, just cut it off. I just went to 4. Okay, then we have. Did you check the box?
I'm checking that.
Your values, I mean, not box. Equals 180. And that one will mess you up, right? It's terrible. I know. And my base here is 1. And I'm going to do 1.699. Again, I'm just truncating. If you're going to round, you round. You either can round or truncate. So you either can round or just cut it off. How do we do? Do we get the same thing? All right, so the next question is going to ask you, it says discuss the right endpoint behavior and the left endpoint behavior in relation to the regression equations. And which model would better represent the data set and why? So we're going to go back and look at our table. I can look at it here. I just wrote down what we. Oh. Mhm.
All right, go back.
Okay. All right. So looking here, our end behavior for both models on the right endpoint, are they both as x goes to positive infinity? What is y doing? Y is also going to positive infinity. So both models have the same right hand behavior. I'm going to write both models, same right hand behavior, right endpoint behavior. Let's be proper. Okay. Now, what about the left? So, like, if I look at the functions, pull them up. If I look at my functions overall, what's taking place? Zoom out. Exponential is decreasing, and this guy here is no, they're increasing. They're increasing. I was like, what? Uh, yeah. Oh, going to the left. What are they heading towards? To zero. Is this one really heading to zero, or did it just stop because that's where the graph cut off at? Yeah. So let's actually get a full view of it. To get a full view of in Desmos is you actually have to put the values as an equation. So you have to actually write it out as y equals or f of x equals. So I have to write it out fully. And I so that I don't make errors, I just copy and paste. Like so that I don't make any errors while doing it, I copy and paste. It makes me make sure I'm like, oh, okay, control copy, control paste. Okay. Then I'm going to do my X, shift 6, and I'm going to go up and copy my B. Control copy. And remember in my notes, I said I truncated. This is part of the reason why I truncate is because if I'm using Desmos or something, I'm going to end up seeing where it goes and stopping. So it really isn't stopping. It's just kind of what it is. Just double check it. Yeah, this was a table. And then it also allows me to open up a table. So I can hit here, and this little feature allows me to see a table of the values. And so if I wasn't sure if it was stopping, I now have a table I can analyze. And what does this tell me after zero? It does what? It becomes undefined. So I'm like, oh yeah, you're really stopping. That's where you are. You can't see the table until you create the equation in Desmos. Does that make sense? Whereas in TI-84, we can send it directly to the graph, to the y equals, which will automatically graph it, automatically create our table. However, in Desmos, in order to see the table of your function, you have to write it out. Okay. So now for sure I can see, okay, well, exponential is continuing. However, the power function stops at zero. My exponential is the red one and it's continuing. Yeah, no, exponential is continuing. However, my power function has a stopping point, right? So that's analyzing your left endpoint. So describing in those words in some format what's happening on the left side. Let's see, how do I want to word it? Say however you want to write it. Exponential as x goes to negative infinity, y is heading to what? Zero. And for the power function, as x goes to, it can't go to negative infinity, does it? X only goes to zero and it stops at y equals zero. So that's describing the difference. Okay. The next thing is when it's asking you to evaluate. If you want to evaluate, sometimes you can follow along the line and find the value. However, it's not that easy at all times. So that's when you want to create the model. So it says here, use the exponential model to find the number of bacteria in the initial sample. Make a prediction for the number of bacteria present at 24 hours. Well, the initial sample means we're at zero, correct? Correct. So that's pretty easy. I can just come here and see what the value of zero is, right? So my initial sample had approximately 180. Agreed? Because it says use the exponential. Now, if it wants me to evaluate, you have a couple ways of evaluating. Way number one is that you could scroll along this line until you find the value you want. So I could scroll until it's possessed.
I literally muted the volume. Like, that's crazy.
It's possessed.
You turn the volume back up.
I don't know what I do when I go over there. All right, so you can zoom out and keep going all the way to 24, right? That's option number one. Option number two is to just create the function model. So I'm going to do the same thing here, but this time I'm finding the exponential. So I'm going to do y equals y. I'm going to actually do f of x so I can plug in f of x equals. And I'm going to come up here. I'm going to copy and paste my exponential. So my a value, copy. And then the b value. I'm listening.
Forget the second equation.
I had both of them in here. My power function and my exponential model. My b value, and then to the x. So now it's on there. So now that I have this function, I now can evaluate it. So if it wants to know what is the value at 24, I can do f parentheses of 24. Instead of having to scroll on this graph to figure it out. Does that make sense? Okay. Your other option is that you can click on it, open up the table, and you can type in 24 on the table, and it's going to do the same thing. So you either can use function notation to evaluate, or you can use the table to evaluate. But either way, in order to get a value without having to scroll all the way to 24, you're going to have to copy and paste and create the function. Does that make sense? Okay. I just want to make sure that I'm giving you all the tools if you choose to use Desmos or TI-84. Obviously, on TI-84, once we run our regression model, we automatically send it to our y equals, right? Which automatically sends it to our graph in our table, and we can easily find the value. There's a couple extra steps if you choose to do it on Desmos.
Good question.
Yes.
How did you find the power function regression model in that? In what way that?
This part? I typed it in. So in our notes, we wrote down the power function model. And I typed in what we wrote. So we wrote y1 for power, tilde, ax1 to the b.
Oh.
And then that's what I typed in to find the power.
But the power function wasn't a thousandths place.
Yeah. All right. So then now for our prediction, we can write down what did we find? Well, what was our initial amount? So based on our model, our y hat, our initial, it equals 180.658. And we're talking about bacteria, right? Okay. And then based on our regression model, after 24 hours, there would be 60,789,462 and 320 hundredths bacteria, roughly. Okay, the last piece is what if I give you your y? How do you find your x? Okay, so if I give you y, so if I want to know for what value will I get 10,000? Exactly, that's exactly what we would do. Tell them again, Emiliana, what are we going to do? We're going to type in y equals 10,000. Because I'm no longer using my power model, I'm just going to go ahead and hide it if that's okay with y'all. And I don't need that one either because it's already on there. Okay, so I'm only looking at the exponential and it says, when does this equal 10,000? So in order to do that, I'm going to zoom out just so I can make sure I see 10,000. All right, so I need to know, what is this value? You could try and scroll and get there, but that's pointless, okay? Just literally, just literally type in y equals 10,000 and it'll tell you, okay? Bam, okay? That's actually a good answer. Okay. Yeah, it'll still be the same, okay? You would keep it at 7.57. So roughly around during the 8th hour, I guess I would say that if you're going to answer the question. Yeah. So during the 8th hour is when the bacteria will be at 10,000. Good point, Emiliano. I agree with you. Okay. Was that terrible to do? No. Now, the only downfall here is that I will say that it does give you that rounded value. It doesn't give you the extended decimals of the 7.57. Unlike if we were to do it in our TI 84, it'll give us as many decimals as we want to look at on the screen for the most part. But that's the gist of this. So, like, questions, comments, concerns? No, this would all be on a calculator part of the test. Yes, yes, yes. That would be cruel. Like, why would we do that? Oh, no, no, no. This would all be on a calculator part of the test. Okay. So we ended up with roughly, I'm just going to write in the 8th hour. Is that cool? In the 8th hour is when the bacteria will have reached 10,000. That's because X is approximately 7.57. All right, so we're going to skip number 8 because it's just more practice. So we're going to skip 8 and we're going to summarize what we know on 9. All right, so as we look right here, it says we're analyzing our data. So notice that if a data has an upward trend and we're looking at the residual. So the data plot is there and these are our two residuals. So we say, okay, this could be linear or exponential. Why can we tell from the residual that linear isn't a good model? Why from the residual can we tell linear is not a good model? It creates a what? A curve, a pattern is created. All right, here we go. So, as we were saying before the announcements came on, Alberto brought up the point that there's a pattern, right? There's a curve pattern that takes place. Because of this curve pattern that we see, right? That tells us that there's a pattern been formed. So, which means a part of the data is nonlinear. Okay. However, when we look at the exponential model, what do we see? It's scattered. It's random, right? It is randomly scattered amongst the data, which tells us that this is probably the better fit. If it's patterned, then that means that what you're trying to use as a regression model isn't a good fit. Yeah. That's a pattern. This one's not. It's evenly scattered. It's randomly scattered around the positive x-axis, which means that this is a better fit. Yes. How we feel? Yeah. All right. The last thing is the cubic model. that we really need to talk about. So making sure we're comfortable with a cubic function model. I feel like at this point, after talking about the cubic, we don't need to do example 11 unless you guys want to. It's supposed to be one you do by yourself. It's a really big one. But if you feel pretty confident in using Desmos or using DI-84, then I won't make you do it. How do we feel? Okay, let's talk about the cubic then and we'll be good. All right, cubic model. So cubic model here, I'm going to write out the Desmos, but I'm going to model it. I'm going to stick to my girl here. I need this moved down. All right. And the reason why I'm telling you this is a cubic model is because once we graph it, we'll see what the shape looks like. So if you're using Desmos for a cubic model, it's going to be y1 tilde ax1 to the third plus bx1 to the second plus cx1 plus d. And that's going to be your cubic rule in Desmos. All right, so we're going to start off with a little bit of review. Average rate of change. What is average rate of change simply? What are the two things we're doing? What are the two math processes for average rate of change? What are the two math operations that take place that we're doing? Should think slow, but what are the math operations we're doing? There's only 4 math operations. Okay, so that's one of them. What's the other one we're doing? We subtract and divide, guys. Average rate of change is just subtracting and dividing, correct? Yes, Miss Jones, because we remember average rate of change. Average rate of change is just subtracting and dividing. So it's saying here, find the average rate of change in cost from 2,000 to 13,000 books. Okay, so from 10 to 2, 10 to 13. So this is your X1, this is your X2, this is your Y1, this is your Y2. Can we calculate AROC? Remember, we don't forget the basics. Oh, perfect. Hudson, they're ready. Okay, so AROC. So we have 167.5 minus 153 divided by 13 minus 10. Someone tell me, what is my AROC? Don't have the calculator. You're going to do it in your head? What is it? 11 point divided by 3. And what do we get? I was like, I don't know.
It's yeah.
I was like, is that not right? That's not right.
I think
That's not right.
yeah, it's 14.5.
So we have 14.5 divided by 3. And what do we get?
8 or 4.3. Why am I 4.8?
That's 167. That's it. Looks like that.
Well, you also can read your own table. So don't try to blame me. All right. Now do remember AROC. Please quickly find the AROC for 18,000 and 20,000. Go.
Bro, I looked at the number wrong.
What happened, Mr. Stats guy?
Find your AROC for got to sneak in some stuff from semester 1 so that we don't forget that information, right? Done? Can someone tell me my average rate of change? 2.6. So that's 2.6, $1,000 per book. So $2,600 per book on it. All right, next is finding the cubic regression model. Is it going to be any different than finding any other regression model? Nope, it's just a different thing that you're typing in. Does that make sense? Or if you're on the handheld, instead of pressing 4 or 5, you're now pressing 6 because that's where cubic is, right? Okay, so really quick, I'm just going to open it, but I'm not going to do it because I feel like you can do it on your own because we're now professional regression models. All right, so remember, we're putting in our data. So I cleared everything out. So we're going to go to Stat, Edit. You put in all your values, your 5, 10, 13, 17. I guess I am doing it. 18, 20, 23, 25, 28. And then we have 135 and 2/10. We have 153. We have 167 and 5/10. We have 172 and 6/10. We have 182 and 5/10. We have 187 and 7/10. We have 180 and 8/10. And we have 193 and 8/10 and 230 and 5/10. Okay. Now we're going to go to Stat Calc and we're doing a cubic, which is 6. If you're in Desmos, you're going to be typing out what I wrote at the top for you. And I'm going to store this. So I alpha trace, and I'm going to store it as equation number 1. Going to hit enter to calculate this bad boy. And it's going to say this is your A, your B, your C, and your D. Once I have those, my values, I can write it down. And now I want you to verify if this is a good model. Is this a good fit? So the way to do that is I can analyze the residual. So if I go to y equals, I'm going to go, second y equals. I'm going to go to my plot. I'm going to turn it on, and I'm going to check the residual. How do I check the residual? Second stat. I'm going to check my residual. And now I'm going to go zoom. And I'm going to do zoom trig so I can see it. What does my residual look like? It looks scattered. It's pretty evenly scattered above and below positive x-axis. So what does that tell me about my cubic model? It's a good fit. It's a decent fit. Okay. Yes. How we feel? All right. And then it says, if you keep going, what is the cost to publish if no books are printed? So the cost at 0. I can go to my table for that, right? Because it's in here. So at 0, what does it cost? $75.15. Remember, in Desmos, you can scroll. So if it on the next part on F, it says, what about 24,000? So I need to go to 24. I can either scroll down to 24. I'm showing you all the different ways you can do it. We can scroll down to 24, which is fine because it's 24, right? Or we could do y equals. Or from the graph, you can go to your graph. Second trace, you can find a value. You can type in 24, hit enter, and it'll do it from there, right? So we can go to graph, second trace, do it there. And then the last spot you can do it from is from the calculator page. In the calculator page, I can do alpha trace, and I want to know the value of 24 for y equals 1. So there are 3 ways that you can find your value, correct? Without you actually having to type or calculate. All right, so we have all these tools in our toolbox for us to be great. Questions, comments, concerns? Yeah, E was the y-intercept. When we went and looked at 0. Yep.
What is that one applied for? 24.
That's the last one on F. It asks at what's the 24,000?
I have one question.
Alright.
Oh, it's going to the one we have at most. How would you fit is the TI?
This one, that's the power one. It's A. So you scroll all the way down to A.
Those 8?
So if you go to second, I'm sorry, go to your stat, and then go all the way down to A.
Alright.
Power. There we go. All right. Do we feel like we need more?
Down to the T.
Okay.